All right, hi guys. So this is our homework number 32. I'm just going to go through it with you guys to see the steps. We've actually learned most of this in the last 2 weeks already, setting up the problems. We've learned all the formulas that we need so far. Now the problem is how to solve it. Most of these questions are going to be working backwards to solve for exponents and then moving forward. Now, for instance, let's take a look at question number 1. If you look at it, the problem here is find the solution of the exponential equation, and we're looking for t. Now, t is in the exponent. So here we go. What we're going to do, I'm going to copy this down. 1.06, 2 to the t is equal to 500,000. Now, in algebra, our idea is to solve for the variable. And hopefully you guys can see along with me that the variable here is our variable t. Now, how am I supposed to get to this t variable? Okay. How am I supposed to get to this t variable? And the goal is to get rid of everybody. We're going to get rid of the 1,000. We're going to get rid of the squared. We're going to get rid of the 106. We got to get rid of everything to solve for t. But it's not going to be from algebra 1. We need our algebra 2 skills here. So let's go ahead and start getting rid of stuff and start off with 1,000. So we're going to get rid of 1,000 first because it's farthest away. We have 1.06. 2 to the t is equal to, we can divide the zeros out. That's going to be 500 for us. Now we can't just divide the 106. Do you guys remember how can we get to the exponent? What special tool have we learned to get to bring down the gods? And hopefully you're going to tell me logs. And that's like what we've been working on. We've been working on strategies to solve for variables. And in this case, the variable is in the exponent position. So I'm going to write log here, log 1.06. 2 to the t equals to log 500. Now you can see I'm actually showing a lot of work here, and I should be expected to see this work from you guys. This 2t goes to the front. 2t log 1.06 is equal to log 500. We can divide the log over. It's 2t is equal to log 500 over log 1.06. This is going to be on a calculator. Let's go ahead and bring up a calculator. Oh, I don't have a calculator. Here we go. So we're going to type this out, 500 log divided by 1.06 log. And I'm going to hit equals first. That's going to give me 106. Then I'm going to divide this by 2. Divide this by this 2 here. So we end up with t is equal to 53.32696. The question asked me to round to the nearest, I think, fourth decimal place. To fourth decimal place. So we're going to take it all the way to here, rounding up. 53.32 rounding up becomes 69, becomes 70. Good. So let's go review our steps that we went to solve for this exponent. First, I got rid of the easy number in front. Would you agree this is 1,000 times? Opposite multiply is divide. That's what we divided over. How do I bring down this exponent, variable and exponent? We have to use log, so I log both sides. Once I log both sides, the 2t goes to the front, pretty easy. Then everything else just divide the log over and calculator works the rest. Okay, let's go ahead and continue this. Next question is a branch of a population of bacteria is growing, and according to this estimate, population is equal to 650 e to the 0.15 t. So this is continuous growth. Estimate when the population will exceed 1,220. Right. So we know that the population of the goal is to get to 1,220. We have an equation here, 650 e to the 0.15 t. Now, we're all set up, good to go. Now, what variable am I solving for? Please acknowledge that this is the exponent t. Now, to solve for the exponents, we're going to have to use logs. But I don't want log right now. We want to first get rid of the easy numbers. Let's get rid of the 650. It's 650 times e. So opposite multiply is divide. So it's 1220 divided by 650. And then we're going to say it's e to the 0.15 t. Okay, great. Now, how do I bring down the exponent? What special log do we use for e? So this is just a quick reminder. We're going to use natural log here. So if I natural log both sides, 1,220,650 is equal to natural log of e to the 0.15 t. Now, the work should say, hey, what happens to natural log of e? These end up canceling out, leaving me natural log of 1,220,650 equals to 0.15 t. And then this is all calculated work. So once you do this a couple of times, it actually becomes pretty mechanical. It's the same stuff every single time. So on the SAT, when you see problems like that, you don't have to freak out. It's like, oh, okay, I've done this before. We're going to natural log this. Why do we use natural log? Is because we had our exponential e. And then we're going to divide this by 0.15. So the t is equal to 4.19755. They want us to round off to at least one decimal place. Give your answer accurate to at least one decimal place. So we're going to say it's going to be 4.2 t. Those are our answers. Yep, that's what we got before. So these questions actually don't take that much time. These are already set up for us, good to go. Now, the next question here is not set up for us. And question number 3 is not set up for us. So we're going to have to set it up ourselves. A fox population in a certain region has an annual growth rate of 9% per year. So our rate is 0.9. Oh, sorry, not 0.9, 0.09, right? That would be 90% per year. It is estimated that the population in the years 2000, so year was 2000, and the population was 9,000. Okay, find the function that models the population in t years for t years after 2000. So we're going to start our t is equal to 0, starting from 2000. So the population model is p is equal to 9,000. That's our starting value. If you remember the equation is p equals to, no, sorry, not p. Because yeah, p is equal to p of t is equal to p naught e to the rt, where p naught is what we call our initial population. So we had 9,000 foxes to start. This is going to be on a continuous growth. They say continuous. Let's see, which one do they want? They want, nope, they want a annual growth rate. They don't want continuous. So we're looking at 9% per year. So it's 1 plus 0.09. This is like compound interest. This is like money. And then our exponent is t years. We can simplify this to be p is equal to 9,000 times 1.09 to the t power. And that's what they have here. Now they want us to estimate the population in 2008. If you read part B, what is the population in 2008? Well, how many years is it from 2000 to 2008? That's going to be 8 years. So we're just going to plug t is equal to 8 and then plug that in here. Just so you guys can have this on your video, we're going to take 9,000 and we're going to multiply this by. Now on my calculator, I have to type things in an awkward way. So I'm going to type 1.09. Oops, darn it, that didn't work out. 0.09. I'm going to take this to the xy of 8 and then mix it all together. So they're going to, after 8 years, the fox population is going to balloon. 2008 is going to be 17933. Yep. And they wanted us to round to the nearest integer. Okay. Oops, these two problems are actually the same. Oops. I'll go ahead and delete one of them. Let me check in case if no one has started it yet, I can delete it. If I can't, I have 2 people in the waiting room. Oops. I thought I admitted Ethan already. That's what my problem was. Give me one moment, please. Question number 3 and 4 are the same, really? Oh no, the second one is different. I'm sorry. Okay. Okay, let's jump to 9 here. Oh, 8, I'm sorry, 8. The wooden artifact from an ancient tomb contains 60% of the carbon 14 that is represented in living trees. How long ago to the nearest year was the artifact made? So these types of problems when it comes to carbon dating, we're going to use our PERT, P equals to P naught E to the RT, or you can change it to N if you want, just depending on which textbook you're using or what you're representing. P is usually population, but the same stuff. It's just whatever you're starting off with. Now, they said we only have 60% left. So let's give ourselves an example. If I start off with 100, and after so many years, we would end up with 60, right? So that's 60% of 100. E to the, we don't know what the rate is, but we know the time of the half-life is, oh no, whoops. Nope, whoops. So we don't know our rate, and we don't know how long it took to get there. So we don't know 2 things. So for these problems, we have to first start with what's given. And what's given here is that last part. The half-life of carbon-14 is 5,730 years. So this can be written as half-life is how much do I end up with to end up, how long does it take me to get to half? E to the R, and then the half-life is 5730. So these half-life equations are always written in this style. You could start off in physics or in chemistry, you learn it writing it this way. 1/2 is equal to R to the T. And the way they get to 1/2 is because they go from 100 to 50, or you could be from 200 to 100, or 14 to 7, right? Regardless, whenever you divide it over, it's going to be 1/2. So we have 1/2 equals E to the R 5730. Now, why do we have to do this? Is because they give you this general idea that you now have 60% left. But what was the rate of decay per year? How fast was this? Decaying? And we never know what the R rate is because it's easier to describe 5,000 years than 0.00033332 rate per year. So it's easier for me to just give you the half-life, the length that it takes to get in half. So then we have to solve this by using natural log because I need to bring down get rid of the E. R5732, 30, I'm sorry. And then now we're just going to take out our calculator to find out what our rate is. Again, these half-life models, they don't ever tell you the rate. You have to find the rate. So I'm going to say 1/2, 1 divided by 2, that's 0.5. I'm going to natural log this. Then I'm going to divide this by 5730. And you'll see it's a very small decimal. The rate of decay is negative 0.0001209. I'm going to go 7 here. That's the rate of decay. And it's so much easier for me to tell you it takes 5,000 years to drop in half rather than tell you this rate of 0.000012097 per year. That's the reason why they always describe these models like this. Okay, so now that we have the rates, we can figure out how long it took to get from 100% to 60%. So now we're going to go back to use this guy here. We know it's 60. If we start off with 100, e to the negative 0.000012097. And then the t-value is what we're solving for. We don't know what t-value is. Then it goes back to every other problem that we've done so far. We divide the 100, and then we're going to get rid of the natural log. 60 over 100 natural log both sides is equal to negative 0.0001209 t. So I'm going to type this in my calculator before I divide over the decimal here. But 60 divided by 100 is 0.6. We're going to natural log that. And then we're going to divide this by a negative 0.0001209. And then we're going to throw a negative sign on this. Looking for my negative sign, plus minus, plus minus. So it tells me it took me 5,000 years, 4,224.8418 years to get to 60 degrees, to get to 60. And they wanted to round to the nearest year, right? That's a little off, actually. It's because of my decimal point. Darn it, I should carry my decimal point even more. Oh no. Let's take a look at my decimals. This could have been 6.8. Let's do 6.8 instead. Let's see if I can get their answer, 6.8. If I put 68.1.0000. Oh, I see a mess. I messed up here because I put a 1 instead of a 7. Oh my goodness. I mistyped in my calculator. And let me delete it. All right, so 0.6 divided by 0.00012097. Let's see if that one gives me a little better. Yeah, there you go. The answer. Wait, was that answer better? Rounding up from 74222.746, rounding up would be give me a 3. Yeah, I think that's the answer that they wanted. I just miscopied the 7. Yeah, that's what they wanted. 4223. Okay, that's finished. We should be able to finish all these questions. Looking at 9, half-life of radium is one. The time for half-life is 1590. If a sample containing 500 milligrams, how much milligrams will be remaining after 3,000 years? Now the problem is, how do you get from 1590 to 3,000? It's not an easy jump. So it's one of those fractions of a jump. So that's why we have to find the rate. So we know how the half-life is equal to e to the RT, where t is 1590. Okay. Again, we end up with half after 1590 years, 1,590 years. So natural log 1/2 equals to r 1590. Now, if you do these problems fast, I mean, if you do these a couple times, you actually can do them pretty fast. Natural log that, and then we divide this by 1590. So the annual rate is negative 0.0004359. We're going to rewrite this problem because they now want to say, hey, the t value is not 1,500 now. We want to say what's after 3,000 years. So we have a starting value of 500, e to the negative 0.0004359, and we're giving ourselves 3,000 years to finish this. And that's all calculator work. You can type that in your calculator. Don't forget the negative sign. Okay, the next section is all about compound interest, and you have to make sure you pick the right equation. Like for instance, number 10 says quarterly. So we have a compounded quarterly is A is equal to P not 1 plus R over N to the NT power. So quarterly means N is equal to 4. That's quarterly. Because I pay 4 times a year. We deposit a initial deposit of P naught is 10,000. And the rate is 3.9%. which is 0.039. Now, do we have everything we need? We have the initial, we have the rate, we have our n. Now, what do we need in the end? They want us to figure out, the last question, part B, is what is our number of years? Hence, our t is equal to 8. So we have everything we need. A is equal to 10,000. 1 plus 0.039 over 4 to the 4 times 8. Because I'm going to pay you 32 times. I'm not just paying you 8 times, 1 per year. I'm paying you 32 times because I pay you 4 times per year. And that's all in the calculator. Now, on your calculator, you have to, again, make sure you know how to use your calculator. Make sure you know how to use your calculator. So on my calculator, I'm actually going to do the parentheses first and then multiply this by 10,000 afterwards. 1 plus 0.039 divided by 4. And that's going to give me what's inside the parentheses. I'm going to take this exponent of 32. 4 times 8 is 32. Then I'm going to multiply this number now by 10,000. So over 8 years, I'm going to go from 10,000 to 13,000. Now, that seems like a lot of money, but over 8 years, if you had bought GameStop maybe, because it tripled in the last week, that could have been a better investment. But with great reward comes great risk. Okay, we're almost done here. Find the time required for the investment of $5,000, right? To grow from 5,000 to 7,200. Okay, with an interest rate of 7.5 per year, compounded quarterly. Quarterly, remember, n is equal to 4. Now they didn't tell me the time. They said find the time. Okay, so we have to find the time now. So our equation is A is equal to P1 plus R over N to the NT. So we know our final, we know our initial. 1 plus our rate, 0.075 over 4 to the 4t. Now, Algebra 2 we've been going through pretty much harder versions of Algebra 1. How do I solve this problem? I'm solving for t. Let's get rid of everything that we can. Let's get rid of the 5,000 first. That's going to be 7,200 over 5,000 is equal to, we can write a big decimal for that, but I'm not. I'm going to write 1 plus 0.075 over 4 to the 4t. Now, how do I bring down the exponents? This takes us back to us solving for logs. This is log of 720 over 5,000 is equal to log of all this. So 4t log of 1 plus 0.075 over 4. Okay, that's all calculator work. So log 7200 over, darn it, that's wrong. Careful about your division sign. This is inside 5,000. Then we're divided by a different log, 1 plus 0.075 over 4 equals to 4t. And you're gonna have to practice doing that on a calculator. You can of course write it separately, leave some, go into decimal places. This could be written as a nice easy decimal. But I'm gonna actually type it as it is. And let's see if it's gonna work out for us. 7200 divided by 5,000 equals, and I'm gonna log this number. Then I'm gonna divide this by, I need to do a parentheses for this one. Parentheses, 1 plus 0.075 divided by 4. Close the parentheses. Okay, that's my percentage rate. Then I'm going to log this number. And I'm going to equals, and that's the mix of the top divided by the bottom log. Then we divide this number by 4. And we're good to go. T is equal to 4.907. And that's the number of years. 4.907. Let's bring it up to the last two. We're kind of running out of time, so I'll kind of run through this. Oh, last three. Okay. The final amount of money is $1,900. The deposit rate was 5.5%. And compounded quarterly. Quarterly is n is equal to 4 times. And the money is left for 8 years. Okay, this one's pretty easy. They just want us to plug it in. 1,900 at a rate of 1 plus 0.055 over 4, because that's a decimal, and 4 times 8. And that's our final value. Now let's hit A. So that one's not really solving, that's just plugging it in. Number 13, find the final amount of money if we start off with 5,500 and deposit at a rate of 4% interest compounded weekly. Weekly. So weekly is 52.04 and 52 times a year, 52. And for 5 years, okay, that's just a set of problem. That's not actually solving. And then the last one, continuous. We have an equation for continuous. If you're depositing $2,000 at a rate of 60% continuously, so e to the r 0.06, and we're going to do for how many years? 10 years. And that's our PERT model. Okay. Principal e to the rate times time. All right. So this is really just working out all the types of problems that we've been dealing with, whether it's continuous, compound interest, half-life, exponential growth, and how to solve them, solving for that t. We used a lot of logs here, working backwards. So if you guys can get used to that, that is kind of, you'll be set up perfectly for pre-calculus and SATs. All right, that's it.